Hey Ms. Parker, welcome to my physics project video. For my experiment, I will be measuring the static friction coefficient between this little pink chair and two different surfaces. My independent variable is the roughness of the surface, which will range from wood to brick. My dependent variable is the static friction coefficient. I expect the brick surface to have a higher static friction coefficient because it is rougher. This is my experimental setup. It includes a digital scale, a pink wooden chair, a protractor, and a wooden surface. The procedure is pretty simple as it involves me massing the wooden chair, then placing the wooden chair on its back on the wooden surface. Then the wooden surface will be raised from one end until it reaches a height at which the wooden chair will begin to slip. The angle between the wooden surface and the ground will then be measured. I will run 3 trials with the wooden surface and 3 trials with the brick surface. So we're going to tear our balance, place our chair. It has a mass of approximately 74 grams. And then we're going to place it on this wooden platform and we're going to measure the angle at which it slips. Alright, you can put down. So that angle is about 30 degrees. Now we're going to use a different platform, but with the same chair, 74 grams. Place it flat on the thing and measure at which angle it slides off. Okay, you go ahead. Hold. Okay, that's good. So that angle was a lot bigger. It was 45 degrees. Here is the data I obtained from my lab. I also found a table with known values for static friction coefficients between different surfaces. I know that these might not be the exact surfaces that I have used for my lab, but they are similar, and so I will use them for my expected values. For my calculations, I first drew a free body diagram, as this was the easiest way to visualize the forces acting on the chair, which is represented as the box. We have 3 main forces keeping the chair at rest: the normal force, the force of gravity, and the force of friction. In this lab, the maximum force of friction was to be used to find the coefficient of static friction. This is at the precise point when the chair would slip and fall, and that angle was recorded in the data table above the calculations. The average angle was used to find the coefficient of static friction. For the wooden surface, it was 31.17 degrees, and for the brick surface, it was 44.33 degrees. The maximum force of friction is equal to the normal force multiplied by the coefficient of static friction. The force of gravity can split up into 2 parts for this lab to equal out the forces and keep the chair at rest. These are force parallel, which is equal to the force of friction, and force perpendicular, equal to the normal force. Force parallel can also be written as mg sine theta, or mass of the object times gravitational acceleration multiplied by the sine of the angle. Force perpendicular is mg cosine theta, which is the same as force parallel, but with cosine instead of sine. These formulas can be used to rearrange the static friction equation as mg sine theta equals mg cosine theta times the coefficient of static friction. The mass and gravitational acceleration cancel out, and sine theta divided by cosine theta is the same as tangent theta. Therefore, the coefficient of static friction is equal to the tangent of the angle right before the chair slips. For the wooden surface, this would be 0.605, and for the brick surface, it would be 0.977. The graph that I have included shows that as the angle right before the chair slips increases, so does the coefficient of static friction. The y-axis represents the coefficient of static friction, while the x-axis represents the angle in degrees. The circle dots represent the wooden surface, and the box dots represent the brick surface. This shows that the wooden surface had a lower coefficient of static friction, while the brick surface's static friction coefficient was higher, just as estimated. The percent error is calculated below the graph. The accepted value for wood on wood ranged from 0.25 to 0.5, so I used the maximum value at 0.5. The percent error for wood was 21%. The accepted value for wood on brick is 0.6, but the calculated value was much higher at 0.977. The percent error for wood on brick was 62.8%. These large percent errors may have been due to the surfaces not being the same as listed in the chart. The more rough a surface, the higher the coefficient of static friction, and this was very true for the brick. This also could have been true for the wooden surface as well. Other examples of error include the surface not being held at the same angle as which the chair fell. This posed a major challenge as the brick was quite heavy and the wood surface kept slipping on the tile. If the experiment were performed with the lighter materials and on a surface that was not as slippery as the tile, the results would be more accurate. I could not find a proper protractor in my house, and the one I used was a little inaccurate, as it would not be 0 degrees on a flat ground. This had no effect on the lab, but the digital scale I used was not very precise, as it only went to the ones place. My hypothesis was correct, as the brick surface had a higher static friction coefficient compared to the wooden surface. The independent variable was the surface that the chair slid on, and I changed it by making the surface rougher. The dependent variable was the coefficient of static friction. This showed that as the surface became rougher, the coefficient of static friction increased.